Okay, so our next speaker will be talking to us about WebAssembly and GHC.
Yeah, hi, I'm Cheng, the current maintainer of the GHC WebAssembly backend. So today I'm going to be introducing the implementation of a feature that I added in GHC 9.10, that is the JavaScript foreign function interface. So I guess we could do a quick live demo here, not by writing any code, but I can show you that we have ported some existing apps that is based on GHC JS and miso framework that is also running on GHC Wasm backend. So here is a little live demo. This is running purely in browser, in WebAssembly, and we can do something like this. The point is not to get to the actual end of the game here, but to demonstrate that we can indeed call JavaScript functions in WebAssembly and vice versa. So miso is supported, and in principle, other GHCJS-based frameworks like Reflex and such should be possible to be ported to WebAssembly as well. If you want to give this feature a try, I encourage you to read the GHC user manual. There is a section of how to use the GHC Wasm backend in the manual, and there is dedicated guide to use the JavaScript FFI feature. And if you want to set up the GHC bin lists to use GHC WebAssembly backend, then we have a repository in the GHC GitLab called GHC Wasm Meta. So this is how you would get started. So first of all, I would like to introduce how we manipulate the JavaScript values in the Haskell heap. So before we landed this JavaScript FFI feature, what we can already do is to compile your Haskell code to a self-contained .wasm module, and that .wasm file can run on any platform with basic support for WASI, the WebAssembly system interface. So that is a lot of platforms, including the browsers, as long as you have a JavaScript implementation of the WASI standard. And yes, and indeed, people have written blog posts on trying to run a WASM module of Haskell in the browser that renders to a canvas without any support for the JavaScript FFI feature. Now, how do we compile Haskell to WebAssembly after all? The most important aspect is that we cross-compile the GHC runtime system, which is in C code, to WebAssembly. And then we have a native code generator for Haskell that starts from CMM and generates the Wasm code that is compatible with the cross-compiled runtime code. The most important aspect of that is that the entire Haskell heap is living in the linear memory of zeros and ones. So what does that mean when we want to target the web browsers? So the kind of data that we can exchange between the JavaScript world and the WebAssembly world is kind of limited. We can pass the simple numerical types, the integers, the floating points between the two sides. We can also pass pointers, but we cannot pass any pointers to the JavaScript heap, to the linear memory. We can only pass a simple integer, which is a pointer to the linear memory. So if you want to exchange data like UTF-8 strings or JSON or whatsoever, you have to allocate your own buffer by calling malloc inside the linear memory, and you have to you do not have to forget to free that buffer. So how hard is it to just pass a JavaScript value to the Haskell world? That is actually pretty hard given our current compilation model. The problem is the JavaScript heap, in order for it to properly do garbage collection, the heap pointers are completely opaque. You cannot just steal a pointer and cast it to a meaningful integer and pass it into the Haskell world. And this is not something unique to JavaScript. If you want to target Haskell to any platform with precise garbage collection, like JavaScript, like Java Virtual Machine, .NET, or whatsoever, then this characteristic will apply. So the GHC runtime system, it cannot manage any pointer without knowledge of the heap structure. So it can only manage the Haskell heap closures within the Haskell address space. It cannot manage any foreign pointers like that. So WebAssembly also has its own extension that supports basic garbage collection, but in order to support that, the current GHC Wasm backend would be completely rewritten. So that is not something we support for the time being. Well, actually, there is a low-tech solution to that. If we cannot store an opaque pointer within the linear memory of zeros and ones, how about we just store unique IDs and maintain the mappings from IDs to actual JavaScript values within the JavaScript world? So that is how we manipulate the JavaScript values on the Haskell heap. So in JavaScript, we have a tiny little module called the JS Val Manager. So it is written in JavaScript, but the interfaces are imported into WebAssembly store. So what it does is that it's a simple key value mapping. The keys are 32-bit unique IDs, and the keys are what we store in the Haskell heap. And then we use CMM to implement a kind of custom heap object called the unlifted JS val hash. The structure of this heap object is rather simple. It's just a closure header plus a unique ID as the key. And then we have a lifted JS val type, which wraps the unlifted JS val hash type. And this is what we use in the user-facing Haskell programs. And how can we create and destroy the JS val values on the Haskell heap? The creation is when you work with a JavaScript import function, and then the import function can return a JS val, and then you have a JavaScript value in the Haskell heap. And it also works the other way around. If you export a Haskell function to the JavaScript world, then you can specify JS val as the export function arguments, and then JS val can be introduced into the Haskell heap this way. And the JS vals in the Haskell heap, they can be eagerly dropped by free JS val. And if you have to explicitly free every JS val existing on the Haskell heap, then the usage experience is not going to be very pleasant. So we also have garbage collection logic of the JS val values. So how does it work? Each JS val hash closure on the Haskell heap, we register a weak pointer with finalizers on it, so we can be sure that when no other Haskell objects are referencing this JS val value, the finalizer will be invoked sometime in the future. And then the JavaScript JS val manager will drop that mapping as well. And of course, the weak pointer must be registered on the unlifted JS val hash object. Otherwise, GHC optimizer is very good at doing worker wrapper transformations that does a lot of unboxing and re-boxing optimizations. So yeah. Is it possible for the Haskell resources to be automatically freed in the JavaScript heap as well? The answer is yes. When we export a Haskell function as a JS function, that JavaScript function object will be registered in a special finalization registry in the JavaScript world. The implication of that is that when no other JavaScript values are pointing to that exported Haskell function, then it will send a signal to the Haskell runtime that's saying that the stable pointer pinning this particular Haskell function can be dropped. So the Haskell resources are automatically freed in the JavaScript world as well. There exist some edge cases when you have cyclic references between the Haskell heap and the JavaScript heap, and in that case, you will have to manually call the free JS val interface to break this cycle. Otherwise, you may have a resource leak. But in practice, this kind of cyclic references should be rare enough, so you don't have to care about it a lot. Some people may say you can't just use vanilla foreign pointer for this purpose, because in Haskell, foreign pointer can also work with your custom finalization logic. The answer is foreign pointer is not very suited for this purpose. First of all, we have JS val support as FFI argument type and return type, so we need custom type checking and desugaring logic. But that is not already working with foreign pointers. And of course, our boxed JS val type is deeply magical. It has some additional metadata field, which is maintained by the GHC RTS, and foreign pointer doesn't support that. So we need our custom JS val logic. So right now, we have the infrastructure to manage the JavaScript values in the linear memory. So we can go to the one layer above that and implement the simplest form of JavaScript FFI, the synchronous variant. So here is a code snippet demonstrating a minimal example of using the JavaScript date API to convert from the Unix timestamp to extract the year component of that Unix timestamp. So in the code snippet, we can use $1 or $2 to refer to the first or second function argument. It's pretty much like GHC JS. The code snippet can be any valid a JavaScript expression or a list of declarations, and it can return the final result to Haskell. So we have to modify several components in the GHC to make it support the JavaScript FFI. So first of all is parsing. We have to allow the JavaScript calling convention when we are targeting WebAssembly. We allow any string literals to be passed and preserved in the Haskell AST. It really should be valid JavaScript, but we do not include a JavaScript AST library in GHC. We do not validate JS syntax here. It is validated later somewhere else. And when type checking, we allow the boxed variants of all the types that is supported in C FFI in the argument and result position. And additionally, we allow the magical JS val type in the arguments and results. And finally, the real interesting part is the desugaring logic. We have to convert this syntax to valid Haskell core, and that will be lowered by one of the backends. Either the C backend or the native code generator, they only work with the C call calling convention or the C API calling convention. They only know how to handle the calls to C functions. They don't know what is JavaScript anyway. So the essential idea is that we can build the entire JavaScript FFI on top of the existing C FFI mechanism. So we have to find a way to rewrite this declaration to something that is working in C. So the basic idea is that we need to generate foreign stubs. What is foreign stubs in GHC anyway? The idea is that when you are desugaring Haskell declarations, the GHC driver can additionally emit small snippets of C code that is compiled and linked together with the Haskell code. It is used in a lot of places, like if you are using cost center profiling, if you're using a C API declaration or Haskell program coverage, then the different kinds of foreign stubs will be generated and linked together. And so we are generating some stub C code that is used to support the JavaScript FFI. So the Haskell declaration, it will be lowered to a C call to generated C function. That is the worker function. The worker function is rather simple. What it really does is that it accepts the Haskell heap objects as the C function arguments, and then it allocates and returns a Haskell heap object as the something that we will receive in Haskell function. And what this C function does is that it calls into a Wasm import, right? So WebAssembly code can import the functions of the host platform into WebAssembly and call it. So and CLang support using the C attribute syntax to specify some C functions are Wasm imports instead. So we are using that property to implement the Wasm imports here. But we have a very important question unanswered. So we have some JavaScript code snippet here, but it is not seen anywhere in this generated C code, and that imported JavaScript code has to come from somewhere, right? So where do we store it and retrieve it? The answer is we can put the JavaScript code snippet in WebAssembly custom sections. So the idea of WebAssembly custom section is that in addition to the normal code and data sections in a WebAssembly object, you can also put arbitrary custom sections, which doesn't mean anything to the linker. So the linker will just concatenate all the custom sections and put it in the final .wasm module. But the custom sections can be post-processed by something after link time to generate the JavaScript snippet, which is used for instantiating that WebAssembly module. So we can use the completely undocumented clown syntax. This is assembly text syntax for the WebAssembly text platform. So we can use the ASM syntax to smuggle this assembly code into C. So we put this JavaScript code snippet into a custom section. And then after linking, we have a post linker script, which extracts this information from the Wasm module. And then we generate a JS module. And that JS module can be used to make this WebAssembly module really work. So this is where the JavaScript code has gone. The rest of the synchronous JavaScript FFI is pretty simple. I mean, for foreign imports, foreign exports works pretty much the same like foreign imports. We also generate a stop C function and then export it to WebAssembly so that when you call that C function, you re-enter the Haskell RTS and perform some Haskell evaluation and get the result. JS val support, we covered it earlier. And one minor detail is we do not support the unlifted FFI arguments and result yet. This is supported in vanilla C FFI, but in JavaScript FFI, we find it simpler to implement only boxed arguments and results. It unifies the import and export logic. And the most important aspect is you do not wish to pay for JavaScript FFI when you don't use it. Before, we can generate self-contained WebAssembly modules, right? And we do not want to lose that ability when we are generating Wasm modules that exist outside of browsers. So what we do is we rely on the rather aggressive link time garbage collection of the Wasm LD linker to strip out the unnecessary JS FFI logic. As long as your program's main entry point and all of its transitive dependencies doesn't use any of the JavaScript FFI features, then you can be sure that the Wasm module that you end up as a linker product will not use any of the JavaScript logic. And this is tested in CI using the GHC test suite because the majority of the test suite is not using anything JavaScript related at all. So this is the synchronous layer of JavaScript FFI. And on top of this layer, we can implement something even more fancy, which is the asynchronous JavaScript FFI. So we want to call fetch API in JavaScript, which is, of course, concurrent. And yeah, we don't have time to introduce the JavaScript concurrency model, so I'll just skip this slide altogether. So essentially, the challenges, yeah, let's see how to introduce this. So let's get to the coolest idea in this slide, although we have only 3 minutes left. So it's possible to implement Haskell thread scheduler on top of the RTS scheduler written in Haskell CMM. The main idea is that you can inspect and manipulate Haskell threads and stacks in Haskell, but you can also manipulate the Haskell run queue in Haskell altogether. So whenever you need to do some blocking operations like calling fetch API in your Haskell code, you fetch it off to a forked thread, and then your main thread will just poll the run queue and see if there is any left work to do, and if so, we are going to be yielding to that other thread for execution so that you can guarantee that the thread that is existing in your business logic can actually make some progress. And how to suspend and resume Haskell computation. Yeah, I don't think we have enough time to introduce that. So let's get to the conclusion part. So the Haskell and JavaScript concurrency models can work really well together. What it really achieves is that in JavaScript, you can await exported Haskell function like the native async function. And in Haskell, you can always block for a JavaScript promise without blocking the entire world. And error on one side can be called as exception on the other side. And if there is only one single takeaway in this talk, then that is you can use Haskell or CMM to write scheduler to manipulate the execution of Haskell threads, and there is a lot of possibility here. Like you can implement new I/O managers in Haskell. You can also assign the concept of thread priority mechanism to Haskell, so you can prioritize executing high priority threads and etc. So yeah.
All right, thank you. Do we have any questions? on the broader topic of Wasm for GHC, what is the current performance overhead that you would typically see? Or do you have any feel for that?
We don't have comprehensive benchmarks using something as principled as nofib, but the Wasm performance is somewhere between the JavaScript backend and native. So that is something that we have seen in practice.
Hey, so you talked about the Haskell depending on JavaScript objects, but you can have JavaScript objects that depend on things in Haskell too, right?
Yes. You can.
What happens when there's a loop?
Then you have to manually use a free JS val to break the cycle. Otherwise, there will be a resource leak. Yeah.
All right, then I guess we will break early. Let's thank our speaker. Oh, we have one more question.
So you had the memory manager for managing JavaScript objects from the Wasm structure. Is that a more general notion? Is it used in other Wasm compilation projects? And sort of, I guess, how general the notion is that?
Nope. I think this is rather specific to the implementation details of the Wasm backend.
Okay, thank you.
All right, then let's thank our speaker and go to lunch.